So we're going to just do a little bit of review from last week. You're going to talk, remember I said I'm going to ask you to talk about the data you're going to use. If you don't have any data, I don't have any data yet. If you do have data, we'll talk just a little bit about what you have. And then we're going to spend the rest of the day talking about statistical power, okay? And it's going to be maybe 2/3 presentation, discussion, and then 1/3 application, where we'll use G-Power to do both the problems in the Cohen article and some other problems that you maybe saw on the very last page of the handout for today, okay? So in terms of last week, 4 levels of measurement. Thank you. Difference between, so from the readings this week, not talked about last week, discrete and continuous data. What's an example of a discrete measurement?
Gender, race.
Category of religious affiliation.
Yeah, that would be discrete. What's another example of something that we would measure that would be discrete? Or how would we define, let's step back just 1 second. How would we define discrete?
Category.
Not qualitative, not necessarily. Like the number of people in this room would be a discrete measure. Why? Or the number of people, yeah. The number of people in this room is a discrete measure, and the reason why is?
There's no half people.
Yeah, because it has to be, it's going to be 1, 2, 3, 4, 15, whatever the number is, right? And so that's discrete. Continuous, on the other hand, would be, Michael? Continuous?
Like time.
Time, sure.
Speed. Weight.
Temperature. There, because we could always, at any...
Additional values between the numbers.
Yeah, there's an infinite number of values between Fahrenheit, 62 and Fahrenheit 63, right? It's infinite. There's an infinite number of that. We may not have a thermometer that can capture infinitely many values, but there, in theory, are infinite values. And so we have discrete data, which will tend to be whole numbers, and we're not able to divide the numbers. And then continuous data, which would be an infinite number of intervals in between any 2 points. Does this make sense? And that's from your what's that?
Chapter 1.
Chapter 1 from the reading today. Yes, thank you. How about why do we do dummy coding? Why do we do? Hang on a second. Why do we do dummy coding? Somebody else? Not Michael. Somebody else? Cameron?
So that we can run a test between group differences with just one word.
Breaking into groups. I don't know. Yeah, I was thinking another word.
Similarities?
I wasn't thinking that word, but Brianna?
Isn't it with like discrete variables? So we can run
Or nominal variables. It wouldn't necessarily have to be discrete variables, because we could, I wouldn't say, Brianna, that would be discrete, because the number of people in this room is discrete, right? But it's also ratio, right? And so don't conflate discrete with nominal or ordinal or interval. I think they can interchange. But we dummy code variables so we can assess between group differences with a nominal level of measurement. Or I think as I articulated it in the slides, for better or for worse, last week, is we can run parametric statistics with nominal level data, yeah? So same thing in both cases. So that's a little bit about why we dummy code variable. How about the how? Not the how in terms of how you click or what you click in SPSS, but at a more abstract level, how is it that we do this? What's one thing that we need to keep in mind? One thing that we need to
K minus 1?
Yeah, the number of groups minus 1 is the number of dummy coded variables that we need to have.
Yeah.
And if you do the number of groups, you're going to try to use those in a parametric statistic. You're going to have problems. It's just going to throw an error message. It might run it, but it's going to remove one of the variables for you. So, and when we talk about regression, we'll talk about, well, which group should we leave out? And we call that the reference group, and we'll talk about which group. And it's not always there's not always a clear case for which group should be left out. But if there is, you should make sure you leave that group out. That would be the reference group. So, for example, if we're doing we're doing an experimental study, and we have control group and experimental group number 1 and experimental group number 2, where we have 2 different manipulations. To me, it would make sense to leave out and make the control group the reference group. Because what we're going to be doing then is comparing experimental 1 with the reference and experimental 2 with the reference, which may not be exactly what you want to do, but my guess is it's probably pretty close to what you want to do. But we're going to talk more about dummy coding as it relates to regression down the road, but we will use dummy coding, or you will use dummy coding in the coming weeks when we start to assess, for example, missingness in your data. You'll have to do some dummy coding, and there's some other things we'll have to use it for before we actually get to regression. So those were my notes from last week that I wanted to review. And so now I want to just take a minute. And next Thursday, right, the 5th of September, not just coming Thursday, but next Thursday, you need to have made an appointment with me and come to my, so if you weren't here last week, see the syllabus. I spell this all out in the syllabus. But you'll need to have made an appointment with me, and we'll meet and talk about your data. You'll want to bring the data on some kind of portable media, or have it in your email or something where you can pull it up, and so we can look at it if we need to. We may not have to, but if we need to, I think it would be helpful if you do that. So by next Thursday, that's like the drop dead day. You have to have it by then. But I assume that some of you probably have made some headway. And so, Michael, do you have data?
Yeah.
What kind of data are you going to, or what are you going to use?
From the NSF grant that I work on.
Okay. Here or in Utah?
Here.
Here, okay. What kind? So you studying?
Studying the ideological website groups and how
Okay.
how like we manipulate credibility and interactivity and
This is with Dr.
Nora.
Dunbar? Yeah,
Yeah.
Good.
and Shane Connolly.
Okay, yeah, great. Sounds very good. So experimental data, not content analytic?
Yeah, experimental.
Okay, good.
I think I probably get like kind of similar thing because I also asked from the number. I'm gonna get the data and see probably give me a little bit more explanation about the data set tomorrow.
Okay, good. And then just make sure, we'll have to talk too, but make sure that you set up an appointment so we can do it. And there's nothing wrong with 2 people using the same data, but your analyses need to be different. So you need to be able, the data set needs to have enough breadth that you can have different dependent variables and different, for the most part, independent variables. There might be some overlap, but for the most part, they'll have to be 2 separate analyses. Aaron, do you have?
I'm meeting with Dr. Johnson this week
Okay,
to
good,
go over some
good.
data from her.
Good, okay, good.
I have data from my master's thesis.
And you studied?
It was study abroad students' perceptions and their actions of post-nationals and what influenced those
Okay.
perceptions.
Okay. How many participants?
330.
So good, yeah. Lots of variables?
Yeah.
Good. And independent variables, so you can, good. Jackie?
I might be using Dr. Vance's inoculation, but then I'm also meeting with Dr. Dunbar tomorrow to see if she has.
Yeah. Inoculation data is good, but can be kind of complex.
That's why I'm.
Yeah, and it depends on, I guess I've been around some of Dr. Vanis's inoculation stuff, and he does it just like Dr. Fowden, and I was around a lot of the stuff that he did, and it can end up being, well, you wouldn't analyze it the same way that they would, so that being said, you could sort of slice out, just time 3 in the data and make something work just with time 3, but you wouldn't be probably looking across the different times.
I met with him on Friday and it looked really confusing, so
Yeah, are you inoculation? Have you studied inoculation?
not briefly.
So just keep that in mind. Yeah. Junil?
Yeah, I got data from Dr. Gay, and
Okay.
data that is a measurement about the journalistic cognition about the changing
Okay.
mediatic
Okay.
environment.
Good.
Well, I have my own data, but I'm not sure if they meet the requirements. So maybe I asked actually Dr. Gay
Yeah.
to.
And we're gonna meet
Yeah,
tomorrow or something, and you just bring it, and
Yeah, sure.
and we can look at it. What did you study?
Political participation and media use.
What's that?
Political participation
Okay.
and media use.
Okay. Good. Rashmi, sorry. Rashmi.
I don't know yet.
Yeah. So look at the syllabus and read that little paragraph there. Somebody in JMC might be able to help you. Who do you work with over there? You have a professor that you work with?
Right now I'm working with Robert.
Yeah, I don't. But if you strike out there, send me an email and we'll have to get something put together fairly quickly in terms of data that is of interest to you, something that you sort of are interested in studying. Likely won't be able to publish anything out of it, but at least it's better than me giving you data that you could care less about and analyzing that data. How do you pronounce? Shagofa?
Yes,
I assume that you don't have data either?
I do.
Oh, you do?
Yeah.
Good. What do you have?
I have visual framing, data about visual framing
Oh, good.
from my thesis.
Okay, good. So content analytic?
Yes.
Yeah, good. And clear independent and dependent variables?
No. I've done classification correlation.
Yeah. Well, you have to be able to say here. So when you look at the syllabus, you'd have to say here are some variables that are dependent variables, and here are some more other variables that are independent variables.
Yeah.
And here's how they sort of fit together theoretically. And so you should think about that, and we can talk about it when we talk. Okay. Michael.
I have two possibilities right now. One is from a class project.
Okay.
A year back,
Yeah.
my remembers sent me the data, but it was only part of it.
Yeah.
So hopefully I'll get all of it, and that's on just how close college students feel to their parents when communicating via text message, we measure
Yeah, cool. It makes
other
sense.
things.
Yeah.
If that doesn't work, I have my thesis data
Okay.
on male friendships.
Okay, good. So in either case, you should make an appointment, and we can meet to talk just briefly. And I think us talking about it here isn't a waste of time because it'll save us some time when we actually meet. I'll have some understanding of the data you're going to use. So, Elena, we are talking about data that we're going to analyze for this class. And I don't know if did you look at the syllabus?
Yes.
And so do you have some ideas of the data that you might use?
Yeah, well, I've spoken with Ryan a little bit about it,
Yeah.
but he
Yeah.
is out of town this week, So, I'm not really sure what the data set is, but he does have one for
Okay,
me to look
good,
at, and it's
good.
some sort of organizational communication.
And something that
measure,
you'd
so-
have interest in?
Yes.
Okay, good. So, and not a problem.
Okay.
Jerry?
I've got a meeting with John on Wednesday afternoon. All the data sets that I have are content analysis, so I'm gonna get with him.
Not that you can't do content analysis. You could,
Okay.
as long as you have clearly articulated, inputs and outputs, independent and dependent variables. So,
Okay.
talk to John, and then if he's got something great, I would make the same cautionary note about inoculation data. But unless you're going to do inoculation research.
No, I think he's got something he's been wanting me to work with him on anyway that is not inoculation, is something
Yeah.
else.
And it's not that it's impossible, and it's really not. But if you're not familiar with the concept of the theory of inoculation, then it just becomes all that more difficult too. So,
Okay.
good job. Yeah.
My data set is one that Joanna and I have been working on, and it is on friendship transgressions. And so it was an experiment and based on severity of transgression and type of friendship, whether it was acquaintance or a best friend. And then we measured things like how do you evaluate that transgression and what strategies are you going to use to condemn that person.
Yeah. Interesting. And so I assume plenty of independent and dependent variables, or for sure dependent variables that you'd be able to. Good. Are you going to do? Because are you going to do all the work?
Well, I didn't figure out submit the homework because I didn't have homework.
If you submitted it, I probably wouldn't even know it. But whatever you want to do.
I have data from that same class.
Okay. Good. So, and it's we can talk about it, And so, whatever you want to do, I'm happy to look at your homework if you want me to, or if you don't want to, I'm indifferent.
I also have data from Dr. Chonia. And it's on serial arguing.
Oh yeah.
I haven't played it a lot with it yet, but there's plenty of scale of
Yeah. Good. Yeah. And other students have used similar data, maybe the same data, so it will work. It'll work good for some.
I have some data that Dr. Banis and I collected last semester, and we manipulated gender of the speaker. It's a tweet.
Yeah.
Gender of the speaker tweet was either humble brag or bragging, and then social status, celebrity, or college student. So I think we've got the IVs. DVs I might be a little bit weak on, but I
There
think
has
it'll
to
be
be
okay.
some. There has to be some.
Oh yeah.
How did you deliver the tweet?
It was just presented as a message in Qualtrics. It says like a male college student sent the following tweet, and then there's the message.
So it wasn't sort of a it was in a lab.
Yeah, it wasn't
Or
as
they were
natural as
at a
it was.
Qualtrics terminal. Good. So again, just period. Make sure you are working on this and make an appointment before next Thursday with me, and we can just confirm that what we don't want to have is the data not halfway through the semester the data just doesn't work, or we find other problems with it. So that's what I want to try to avoid. All right? We're good? So I want to talk about power, and sort of my modus operandi is I expect that if you have questions from the reading, you'll stop me dead. Stop me dead? No, you'll stop me mid-sentence and ask questions. If you have questions, I won't ask if you have questions. I'll just assume that you all can ask the questions if you have questions. But and then the other, we get through what we get through each week. And so I'd rather take more time and get through less material and have us understand it than be on some march through the material just so I can get through all the slides in a given day, and then have people leave here with questions unanswered or confusion or whatever. So there are no bad questions. There are not too many questions. So just keep that in mind, and we'll definitely be behind as we move forward. I mean, be behind meaning we're going to start the week finishing the previous week's material. I don't know if that's the case here, but it will be the case as we move forward. And I'm okay with that. We have at least one built-in day to catch up, and I think there might be a built-in day at the end, or at the end, if we're done, we're done, and what we don't get through, we don't get through, okay? So let's talk about statistical power, and maybe start with a question. Why do we care about statistical power? Why do we care about it?
So we can make type 2 errors.
Right. Low statistical power would suggest that we're going to make a type 2 error, and we don't want to make errors in our inference. Correct. Other reasons why we want to avoid type 2 errors. What's a type 2 error, by the way?
Rejecting there's something there.
I'm sorry.
Rejecting it's accepting the null when there's something actually happening.
Yes, and so and we can talk in terms of null hypothesis in this class if that works for you, but we don't have to. I know it's if I were a purist in terms of probability and in terms of hypothesis testing, I'd be like married to the null hypothesis, because that's really what we're testing, right? We're never testing the hypothesis. We're only testing the null, and because our statistics only deal with chance events, right? We don't have statistics for non-chance events. We only have statistics for chance events, and so we're always testing the null. But I'm not. So we can talk in terms of null, or we can talk in terms of hypothesis. Whatever makes sense to you and me is the language that I think we should use. So avoid type 2 errors. What else?
Make sure that we have accurate results.
Sure. Again, we don't want to make type 2 errors, right? And that would be an inaccurate result. What's another reason why we should care about power analysis?
It's good in planning research design. It's good in planning research design because then you know what sample size you need to get to have enough power.
Yeah. And so along those same lines, how else will it help in terms of planning?
Sample size.
Sample size and what else?
Bit size.
What's that?
Bit size.
Sort of, but there's something else I was thinking about.
Cell size?
Yes, but what else?
Your significance criterion.
Sure, think more broadly. What if we're doing power analysis, it should allow us to make good use of fill in the blank.
Conclusion.
No. Resources? So we don't end up, we need, our power analysis says we need n equals 100, and we collect 250. Maybe we don't think of that as wasted resources, but it is, right? Your energy and the energy of the people who. And so I would say that would be another reason why we should care about power analysis. So you've seen this before. The Murphy article had this in it. I probably changed. He probably talked about it in terms of null hypothesis. This is in terms of just conclusions of the study. Anybody know what they call? This table, this 2x2 table? What do we call that kind of table? It's called the confusion matrix. So we're going to start the class with, and it's not a confusion matrix just because it's talking about outcomes of statistical tests, but as a more general term, a 2x2 table is referred to as a confusion matrix for, I'm not sure why it's more confusing than a 3x3 matrix, but that's the vernacular that gets attached to it. So for the 2 rows, we have the conclusion of the study, right? So what did the study conclude? Did you find no effect? Or did you find an effect, right? So that's the conclusion. That's what you concluded in the research that you did. Do we know this? Do we know what's true in the population?
Only if
On-
the defined population is really small, and we collected the entire population.
Yeah, and likely then we wouldn't have to redo, well, likely somebody else would have already done it. Well, we wouldn't be at this stage, we would be one stage past this because we would have already done it. But and we don't know this, right? This is unknown to us. This is hypothetically or theoretically or as known by the gods. This is what is true in the population. And the population is there's no effect, or the population in the population there really is something going on between those two variables. And so our study concludes no effect. And if in fact that is true, we've made the correct conclusion, right? That's a good place to be. Maybe not so good for your tenure case, because what?
Can't publish it.
Well, not necessarily. You can't. It's not that you can't publish it. We tend to bias non-significant results, or the bias is towards publishing results that are significant, right? And so, but in terms of the scientific, the enterprise of science, that's good, right? We did a study, we found there's no conclusion, or there's no effect. There isn't a fact, no effect. That's the correct conclusion. The probability of that is 1 minus alpha. And if we set alpha at 0.05, it's, we have 95% chance of being there, right? The other correct conclusion is there is an effect we find in our study, and that is in fact the case in the population. And so again, correct conclusion, good thing. The likelihood of that is 1 minus beta. And beta is usually set at, what? What's that?
0.2, since they say power needs to be at 0.8.
Yeah, and so this is beta would be 0.2, which would give us 1 minus 0.2. Beta would be 0.8. Is that right? Help me out. So if we have this is power right here, right? So this is right. So this is 0.8.
Power is supposed to be 0.8.
And so this is going to be 0.2, and that means this is going to be 0.2. Sorry. All right, everybody good except for me? So then the two errors, which I assume everybody is familiar with, and we talked about one of them, is our study concludes effect, and there is no effect, right? We call that a type 1 error. And the probability of that is set by alpha, so 0.05 or whatever we set alpha to. And then type 2 error is we conclude there's no effect, but there actually is, we missed it, right? There is actually something going on. That would be a type 2 error, right? So everybody's good with that? Which of those two errors do we want to avoid the most? And why? Huh?
It depends on what, like, were you talking like specifically for research or for a whole discipline?
What's the difference?
Because well, one of the reasons that the type 1 error can like lead down to entire research agendas, because whenever we think that there's an effect and there really isn't, then it's like a wrong research enterprise that leads us, ways to throwing.
Yeah.
But whereas the way I understand type 2 is like more focused on the individual research.
More focused on what?
On the individual research project.
But with type 2, if you're saying there's no effect when there actually is, then there's a chance, particularly in the sciences, that you have a new medicine that's going to solve something, and you go, nothing here, and you totally miss it. A lot of people could get hurt, die, whatever, because you didn't go far enough.
I like the idea of putting it into medical terms, and so if we were testing drugs to cure cancer, yeah, say that's the example. Here, we tell people they're going to be cured, but they're dead in 6 months, right? And here, we tell them, sorry, we have no help for you today, but we could have given them a pill and they would have been cured of cancer, right?
So they're still gonna die.
Right, they're heirs, right? We're not doing well. So which of those two would we want to avoid? How many people think type 1? How many people think type 2? How many people think it depends? You've got to put both hands up. No, I'm just kidding. What do we as a discipline do? How do we prioritize these two heirs?
I would say we focus on type 1.
Why do you say that?
Well, I mean, the readings are kind of old, but the readings talk about how a lot of if you do power analysis for all these things, it was really ridiculously low, which would mean that the beta type 2 error is high. But a lot of times you focus on what you're going to set your alpha at. So is it 0.05, is it 0.01, 0.001? So we focus, it seems like we focus a lot on setting the alpha as minimum.
Yeah. So you say that we tend to focus more heavily on avoiding type 2 errors as opposed to avoiding type 1 errors,
Avoiding type
as
1 errors.
opposed to avoiding type 2 errors. Yeah?
If you avoid type 1 error, then you're erring on the side of caution, right? Oh,
Well, then you increase your likelihood of making type 2 error, right? So, right?
well, I mean, I guess you're choosing
Damned if you
between
do
the
and
lesser
damned-
of two evils.
Sure. So your point is?
I would err on the side of caution more. I mean, I would
Meaning-
rather say I don't have anything and be wrong.
Even if you put the drug back in the file cabinet
Yeah,
and
and then you
say,
can find something else maybe that.
It's
I mean,
supposed to be-
I'd rather
that's
do
one
that.
theory for sure. Yeah, right. Good, Michael. Sorry.
Well, and when you're publishing something, you have to provide evidence, and that's what we're more concerned with rather than, I don't know, showing an effect. Does that make sense?
Yes, that makes sense.
Because
The,
you're
the
gonna
two of them are
claim-
intermingled, though,
If
right?
you're going to make a claim, you're going to have to build evidence for that claim.
Sure.
And if you err on the side of caution in that way, then your evidence will be stronger as opposed to, I mean, even if you're making type 2 error more often, the conclusions that you're reaching are going to have stronger evidence for them because you have been so stringent
Yeah.
in avoiding type 1
Yeah.
error. Does that make sense?
So which error would you want to work hardest at trying to avoid, Elena?
Type 1.
Type 1.
Yeah.
Yeah.
Because then you know if you have avoided type 1 error, then the conclusion that you've reached is super solid.
Okay, so we've heard from two people who said type 1. Those of you who raised your hand with type 2, unless they persuaded you to think differently, tell me why type 2 we should work harder to avoid type 2. Who said that? Who read? Jerry.
I'll go back.
Thank you.
Point to one of the, to this article here, from Murphy.
Yeah.
I believe he points out the studies on use of aspirin to avoid heart attacks. That mentioned a couple times in the article. If we just did 10 people, then you're going to have a type 2 error because it doesn't show up. But if you did 600 people, then we see this, and now we have this as a treatment for people. Just go take an aspirin, and it helps. So for that, from that perspective, I would much rather avoid the type 2 than the type 1 because I see the benefit from really trying to avoid the type 2.
But isn't that also assuming that your effect is something positive? Or negative, let me think. That you're assuming the effect that the medicine is going to do something good. And so you want to find an effect. So a type 2 error. If the effect is positive, a type 2 error is worse. Because it means you're not helping people. But if your effect has a negative result.
For example?
Well, sure, gives them cancer, into the health.
Yeah. The aspirin gives you cancer instead of
Yeah.
helping with heart disease or whatever. Yeah.
So you're saying that Jerry's reasoning is still it depends.
Yes.
But go ahead.
I think type 2 error is the one we should kind of try harder to avoid.
Yeah. Why?
because, well, like, for conducting research, we put a lot of energy, efforts, and money. And if we kind of just reject if we just kind of say no effect while it has some effect, we kind of waste those things.
But if it's in fact the case, if there's no effect, isn't that a good thing that we say that?
I think people.
But I'm sorry, I was gonna say, you're gonna have to be able to say it with power though, to prove that we actually don't have anything here and we need to stop and move on.
Elena, were you going to add something?
All I was going to say is with type 1, it's the reason that we're concerned with type 1 is because people don't want to have like poor credibility in the research community. So that's why I think historically we've been concerned with being overcautious, because if you're making claims that are in the next study considered like wrong, obviously, then you're going to lose credibility as a researcher. So that's why we.
And the reason why we don't have that problem here?
Because you're not reporting the effects.
Because there's a bias, right? We're not.
You're not going to have a study.
Right,
You're not going to write an article about a non-effect. Well, no, maybe, but.
But yeah, it's less likely for sure. Well, we know this is 0.05 traditionally, right? This is 0.2 traditionally. That's 4 times greater than this, right? 0.2 is 4 times greater than 0.05. And so we place a much greater emphasis on avoiding type 1 error than avoiding type 2 error, for better or for worse. And so whatever position you take is the position you take or took. But as the enterprise, as this thing that we call science, at least in the social sciences, that's how we calibrate those errors. 0.05 and 0.2, and so much greater emphasis on avoiding type 1 error than avoiding type 2 error. Does it make sense? So but again, that shouldn't change your opinion. That's just the fact in terms of what we do. And maybe what we're doing and what we've been doing for a long time is just wrong, and you might be right. Who's to say that? But those are the facts as they are currently. Does it make sense? So it's good that it seems like everybody is familiar with the terminology type 1, type 2 error, and that's the takeaway. So as we move forward, we can confidently talk about confidently talk about those 2 types of errors. So there are 2, 4, 6 definitions of power. There's not one that's right or wrong. What I would encourage you to do is to find a definition that works for you. And you really should sort of commit that. It needs to be a definition that this works for me. So for me, it was the probability of not making a type 2 error. I don't know if that one's up there now. Oh, the very bottom one. That's the one that early on made the most sense to me. And it's the one that I just sort of have stuck with since graduate school. So you should think about a definition that works for you for statistical power, and then you sort of commit that to so you have some understanding, and you can easily discuss it, or if somebody for whatever reason in general exam defenses, people bring up statistical power probably more than any other one statistics topic. I'm not sure why. But it comes up with some, and some students, probably students that were in this class, and I gave the same lecture to, hey, you should commit one of these. They're not able to sort of come up with what a good definition of, or a useful definition, or a credible definition of statistical power is. Okay, makes sense? So we want to talk about the things that determine statistical power. And the first, of course, is the level that we set alpha at. And so Latin, ceteris paribus, all things being equal. All things being equal, making alpha less strict will increase our power. So if we move alpha from 0.05 to 0.10, we necessarily increase, if you keep everything else the same, ceteris paribus, then statistical power will go up. Right? Make sense? But there's no free lunches, right? And the price you're going to pay for lunch is increased likelihood of making a type 1 error if you increase your statistical, your alpha level from 0.05 to 0.10 or 0.15. Does it make sense? And so this is just, and these graphs are made with G-power, so if you are bored some afternoon and you want to make graphs that help you understand power, which who wouldn't, you can do these in, so, but it just, the test isn't all that important, but you can see here and in the handout in front of you what the statistical test is that we're looking at. And we're varying alpha from 0.001, very stringent, to 0.15. And there's diminishing returns, though, right? The level of power increases very quickly from 0.001 out to maybe somewhere between 0.05 and 0.07. And then this line is never flat. There's always some slope to it, but it tends to, the slope is diminishing, right? And so we can clearly see that as we make alpha less stringent, 0.001 to 0.15, we're going to have increased levels of power. Can power ever be 1.0? It can only approach 1. It will never, if you check the little box in SPSS to tell it to give you power, sometimes it does print out 1, but it's not 1. It can only approach, but it can get infinitely close, and we would say it's asymptotic, and that this line can get closer and closer and closer and closer and closer and closer to 1. But at any point that you're at any one point, no matter how close you are to 1, there's an infinite number of points between that point and 1, just depending on how fine-grained you want to be, right? So it can only approach 1. It can never actually be 1. Jerry, did you have a question?
I did. I just wanted to double check. This graph, is that going to be true for every single study? No matter what you're studying? Or...
Indeed. As you change the test from a t-test to regression to ANOVA to chi-square, whatever it is, doesn't matter what the test is, the graph will look different depending on the n and where you start in terms of alpha, but it's always going to have a slope that eventually approaches 1, but it's the slope gets less steep as you get closer to, as alpha increases. And never will it be flat, but it just, the slope is decreasing. Make sense?
Yes.
Long answer to a good question. Other questions that I can give long answers to? Short answers to? So far, so good?
So what does that mean if we approach to number 1, the care?
Very high power.
The power formula is 1 minus p. So if we take 1 minus 1, then it should be 0.
But it's never going to be 1.
Oh.
It can be 0.99 to 10 decimal places, but that's not 1, right? It'll never be 1 minus 1. 1 minus some number very, very infinitely close to 1, but that's as best as it's going to get. Oh, that's as close as it's going to get. Does it make sense?
Yeah.
Good. Other questions? And so, maybe I was thinking of Jerry's question when G-power, and I was bored one afternoon, and so I made another graph to go along with this graph, I also varied the effect size. And so we can see that that slope isn't always going to look like this